to Spain, and I'm waiting for the music. So the next presentation will be about power electronics for green hydrogen production. And we have the chance to see and to hear the Hydrogen Business Unit Director of the Ingeteam, Power Technology team. And his name is Harkaitz Ibaiondo. Ibaiondo, I practice.
Thank you. Okay, thank you very much. Thank you for coming. So we don't have too much time, so I go very quickly. You will have the presentation online from the Ingeteam website, so you can have all the details there. So I have some slides about Ingeteam. It's a company located in the north of Spain, in the Basque country, with more than 4,000 employees and with present in 24 countries, and founded by 4 engineers and with very much R&D mindset. We have 9 gigawatt production capacity in similar products that we are going to be presenting today. We have manufacturing facilities in Spain, in India, in the States, and in Brazil. So Ingeteam is present in several sectors, let's say. Wherever power conversion is there, we have power electronics there. We are very strong in wind and solar, traction, marine, any application where electrons are supplied. So in energy sector, we have more than 25 years in energy sector, with more than 80 gigawatts connected to the grid already. And we have also like gigawatt scale plants in the Middle East, one big one also in Australia. So we do know very well the connection to the grid to very high power plants. So in terms of hydrogen, we started 15 years ago developing our own electrolyzer. That was an alkaline pressurized electrolyzer, which is still working in the National Center in Spain, in Puerto Llano. However, we decided to stop that project in 2012. And now we decided to focus on power electronics. However, we do know very well the technology of the electrolyzer, how we have to supply it, and how is the influence of the power electronics on the efficiency and the life of the electrolyzer. Sorry. So I go very quickly in the main presentation of the electrolyzer. You know, it's a device to produce hydrogen from water. Usually it's a low voltage device. Low voltage meaning between 200 volts and 1500 volts, the highest one in the market right now. And very high currents. So voltage, low voltage, very high current. So then right now we connect them usually to the grid, to the national grid. However, we are seeing a tendency to connect to like island mode grid or auto production grids. So you generate some point in your own grid and you consume in another point of your own grid. So this is the one on the left, the bottom. And then, of course, we can also connect the electrolyzer directly to the source, either the photovoltaic plant or the turbine. So in some cases you have an AC/DC if you are connected to the grid, to the AC grid. Sometimes you have a DC/DC if you are connected to the solar panels. So there is a great debate how is better to connect the electrolyzer. the debate is still open, but we see a lot of advantages if it's off-grid, not connected to the grid, because you don't need the permitting to the point of connection. You have only one conversion instead of two. And however, there are also some disadvantages in terms of the distance between the electrolyzer and the source. As it is low voltage and high current, you want them to be very close. So it's still case to case. You have to study how is the best connection. But it's true that these off-grid connections allow you to have hydrogen production where there is no grid, there is no infrastructure. So some islands, peninsulas, some places where there is no high voltage grid could be connected directly. So I go quickly. So there are different topologies to connect electrolyte to supply the electron to the electrolyzer. So the traditional one will be the SCR, the thyristor-based bridge, which is a technology from the 70s, very well known. However, there is a consumption of reactive power, so the power factor is not very good. And also there are harmonics, which are not very good for the grid. So in high power applications, the thyristor by itself, we think that it's not going to meet the grid codes of the grid. So then we have the active front end, the IGBT-based inverter, which is very well known in the market. That's the one that is used in wind conversion or solar conversion. And this is a topology that provides a power factor, a unity power factor, and very good harmonics. Something in the middle, we will have the diode rectifier with a DC-DC back converter. This is something in the middle. It's a little bit better for the grid than the thyristor, and it's very good for the DC ripple in the electrolyzer side. So it's something in the middle. And this IGBT solution is also, I mean, it's very good, but it has some disadvantages, like the current density and some problems with the topology that is a step-up topology, so you can always increase the voltage on the electrolyzer but not decrease it. So that means that you have to oversize the converter for the electrolyzer. So we believe that in the future we will be seeing the current source converter, the one on the top on the right, which has the advantages of the thyristor and the advantages of the IGBT. However, this is not industrially still very known, let's say, so we believe that will become in 3 years. So we'll go quickly on the different thyristor-based bridges, depending on the number of pulses. In terms of the thyristor, as I mentioned, we think that we will need an STATCOM, which is a reactive power compensator and active filter. So for big plants, the thyristor is not going to be a solution by itself, but combined with the STATCOM could be a good solution. So I go quickly on those two. So this is a comparison on the different current ripple in the DC side. So you can see from the 6 pulse, 12 pulse, or IGBT-based converters. So the current for the electrolyzer is nearly perfect in the IGBT solution. And that has influence on the efficiency of the electrolyzer, of course. In terms of the grid, in terms of the AC voltage and current, you can see also that from the 6 pulse to the IGBT, how the sinusoidal becomes perfect, and also the voltage and the current are synchronized, so the power factor is unity, and this is very important for big plants. So, table of comparison, you can study it afterwards. So which one is better? It depends. It depends in many things. So this is not a clarification. It's just to see the complete possibilities. So depending if it's depending the voltage of the electrolyzer, depending the grid that you are connected, depending the power. So you have to study case by case which topology is the best. The one that we are commercializing already and we think it's a very good solution is the IGBT-based solution. In this one, which is a skid solution, 40 feet skid solution, where you have the transformer, you have the rectifier, you have the switchgear, which is optional, and you have the low voltage cabinets. We started with this, but we saw that electrolyzer needed still more power. So we went to the one of the top, which doubles the current of the previous one, reaching 12,000 amps, which is the highest current density in the market right now for IGBTs, we believe. And this is the product based on IGBT. Based on Thyristor plus StatCon, we will also have some products already available. And the one for current source converters, we have a similar one, but it is not for low voltage. So we are under development the low voltage version. So that's a little bit what I had to say. Being quick, I've been too fast, but I hope there are questions so I can develop any point that you want. In any case, you can visit us in C31 over there, and you can download the presentation in the website. So if there is any question.
Yeah. Thanks for this nice conversation.
Thank you.
Presentation, conversation. Maybe we can have a little conversation. There's one question.
Thank you. Very, very nice talk. But first time I saw it in a very clear manner of exactly comparison between the different solutions. Just a question, if we connect directly to the wind and not to the grid, then what will be the effect of you have higher harmonics or stuff like that, like in the Thyristor case?
Yeah, good question. To connect directly to a wind turbine, you mean? I don't think that the Thyristor could have the dynamic that it's needed for direct connection to the turbine. That's one point. And the other one is that the harmonics that the Thyristor rectifier is consuming, the turbine inverter has to provide them. So it's extra load for the inverter in the turbine and also for the cables in between. So you don't want thyristors in a this kind of grid.
So you still recommend IGBT even for a direct connection to a wind turbine?
I think for the grid, the best one is the IGBT. However, the IGBT cannot work is not very competitive for low voltage electrolyzers. So if you have, let's say, 400, 500 volts electrolyzer, then something mixed between the IGBT plus DC-DC converter will be optimal. Or diode. It's not so easy. It depends on the voltage and the grid and the power. More questions?
So, thanks a lot.
Thank you.
Harkaitz, Ibaiondo. So, yeah, give an applause.